Okay, so coming from Stanford, I learned that you need slogans. And this one is trivially true, unlike ER equals EPR, which was pointed out to me is true if and only if P equals 1. So this is cardi entropy. And this, as you may guess, is Casimir energy. And I can end my talk now because this is obviously true. So let's get started. Just to set conventions and things, I'll go through quickly the derivation. You can fall asleep now and take the break between the two talks. If you want of the 1 plus 1 dimensional cardi formula, so ordinary 2D CFT. And again, this is just a set convention. So we imagine we have a 2-dimensional CFT on a torus working in Euclidean signature. And don't be picky if you know the derivation and are unhappy about the way I'm presenting it, because at the end of the day, the right answer will come out, and we don't really have to worry about it. When I get to new stuff, then you can nitpick if you want, but unless something is profoundly confusing, let's just try and get through this. Okay, so the idea is you have two cycles of the torus, length L and length beta. This is supposed to be like the inverse temperature. And then you imagine, from the Euclidean path integral point of view, swapping your two cycles and imagine quantizing in a different direction. And then you can do a scale transformation by L over beta, get a formula for the degeneracy of states in terms of the anomalies of the theory. Here the central charge appears. Okay? And this is hard to do, and we sort of know that we can't do it if you just go to a CFT in higher dimensions. So I'm going to ignore trying to get an expression in terms of the anomaly or anomalies of the theory. As the slogan says over there, I'm actually going to try and get a formula just in terms of some sort of ground state energy and see if I could use that for anything useful. All right, so let's proceed with that. Let me just erase this to make room.
It's also part of the Stanford tradition to explain a little more strongly how this formula is going to solve great problems in theoretical physics.
Yeah, I haven't quite adopted
it. Do something useful.
Yeah, so in a certain sense, I should probably say where I'm going with this. In a certain sense, I want to try and get it. Okay, so this is reproducing the entropy of a BTZ black hole. In a certain sense, I want to try and reproduce the entropy of ADS black brains in higher dimensions. So that's the idea. Okay, so all right, there are two ways I can generalize now. One is to go to higher dimensions, and the other way is to associate a anomalous dimension to the stress energy tensor, which is related to what people call hyperscaling violating theories. Let me just go straight to the higher dimensional case because I worry that I won't have enough time. So let's go straight to a D plus 1 dimensional CFT. Okay? So I'm going to redraw the picture. We have L, beta. Now, and the derivation that I do here is not going to be the fastest way to get at the result, but I feel like this is maybe a more pedagogical way to do this, so I'll do it this way. So now I imagine D directions of length L infinity, which is meant to be large compared to the other directions. Okay? Then I'm basically going to do the same steps. I'm going to swap the two cycles, the temperature cycle and this length L.
Sorry, Edgar, what's the topology now?
Torus.
So
D plus 1 dimensional Euclidean torus.
Okay,
Yeah.
so that wouldn't be the thing for black holes, but
Be the thing for black brains. Yeah. Well, L infinity is large. Yeah, it's the thing for black brains.
You mean to put
Is
an
the
L
top
on
beta and a capital L in your diagram?
What? Sorry. Were you saying the same thing?
Same thing.
Okay. Good.
I'm confused. Don't we know how to calculate the entropy of black brains using ADS CFT? Or
he wants to do a CFT. He's checking ADS CFT by doing like what happened over here.
Yeah, it's going to be
CFT
the analog of
derivation.
this calculation.
Of the Shaghoulian.
I see. So the point is to get. But the nice thing here is you could get C from something else, right? So
Yeah. Here I'm going to get I'm going to get evac from something else.
Oh, okay.
Yeah. Okay, so, but before we get there, let's just stick to CFTs. So there we go. I'm going to do the same thing. Whoops, sorry. Keep wanting to put beta up there. I'm going to do this scale transformation. And the key difference here is that this, because I have new directions, this actually scales up my other very large directions by a factor of L over beta. Okay? So if we want to write the partition function now, again, this equation is probably going to go all the way over there because I'm going to be annoying in writing it. 0 to L, 0 to L infinity, d minus 1 y. So I've just split this up. X refers to the direction along this. This is going to be the important direction. The y's are the directions along these large S1s. So then I'm going to do the swap. So it's going to go from 0 to beta now. This guy hasn't changed yet because I haven't done a scale transformation. I will in a second. Okay. Now I'm going to do the scale transformation. Again, I'm going to call it lambda just to fit it in here. Beta, lambda, dx, 0 to L infinity, lambda, the d minus 1, d minus 1, y. I might not even have enough room. Okay, you can see that this is obviously equal to this because the stress energy tensor has dimension d plus 1, so you can pull out those lambdas and cancel them and end up right back where you started. So far, these are just true equations. And okay, I can write this now as some z tilde. I'll define what I mean by z tilde at L squared over beta. So what's z tilde? So let me define z and z tilde. Z is the partition function on a spatial S1. That's this one here, this length L. Cross, I'm going to call it a plane just because I want to indicate that the directions are large. If that confuses you, turn it into a large torus. If a large torus confuses you, turn it back into a large plane. So you can do this correctly. It's just for compactness. Let's write it this way, and I'll write L infinity here because the size of the directions there is L infinity. That's the starting partition function. And over here, this is the partition function of the same theory. And you can think about it again, that's on a S1 of size L, but now the large planar directions are scaled up. Okay? So, great. What do we want to do now? Well, now we'll use I'll call it fact, that if these directions are really large compared to L and beta and L squared over beta, and all that business, then the log of the partition function is extensive. Okay, it should scale like the volume of the background that it's on. So since it's extensive, I'm basically, let me write that. That's v d minus 1. It's going to be extensive in these directions. I mean, L can be of order the size of beta, so if it gets small, it's not necessarily going to be extensive in that direction, but it's going to be extensive in the other ones. So I'm going to use that to pull out these factors of L over beta and return the partition function to the original background that it was on. So that means log of z tilde of beta is equal to L over beta to the d minus 1 log of z, sorry, let me call it L squared over beta. L squared over beta, L squared over beta. Okay? So I've just, again, used extensivity to pull out these factors of L over beta so that I can write z in terms of z. So altogether, what does this give? This gives that the log of the partition function at inverse temperature beta is equal to L over beta to the d minus 1 times the log of the partition function at L squared over beta. Okay, what does this look like? This kind of looks like that it might be modular form. It has a weight, right? The log of the partition function transforms under a modular transformation with a weight. And indeed, if you want to go through and check, you can show, now let me define this modular parameter tau. So tau is really the modular parameter associated to this two-dimensional torus of beta and L. And then these are just some planar directions, which I assume are large, and so I'm not going to care about symmetries related to those. So tau is the modular parameter of this S1 cross S1. You can show that under a general SL2Z transformation, the log of the partition function transforms this way. I should say, by the way, this is all pretty recent. I was doing some of these calculations in the past several days, so it's not 100% guaranteed to be right. But you guys can spot me and point out if you think something is wrong. But the thing I'm going to get at is right. The final answer is we're going to check it several times, and the final answer is going to be correct. But using these fancy words, I don't know, maybe there's a sign I missed or something. Okay, so this looks like it transforms as the absolute value of a modular form of weight d minus 1. Okay?
It's usually the partition function, not the log of the partition function.
That what?
Transforms like a modular form.
In 1 plus 1 dimensions? Or higher?
Yeah.
In 1 plus 1 dimensions, it just doesn't have a weight. Right? So it's like a...
Well, if you consider it a correlation function instead of a partition function. Okay, never mind.
Okay.
It's just that the one that introduces the weight.
Yeah. Probably use it. Yeah, probably shouldn't use these words because really it's exactly what she just said. There's just some volume factor that pulls out these factors. Okay, so the absolute value of a modular form. What does that mean? That means you could define a modular invariant thing. You can define a modular. So let me call it F. You can define a modular invariant object by hitting it with the imaginary part of tau, because the imaginary part of tau transforms with a certain weight times the log of z of tau. Okay, so this guy is modular invariant. And, in for example, 3 plus 1 dimensions, this is like the ordinary free energy. This is the temperature log of the partition function. Okay? Great. So there we go. We have this invariance. Let me go back over here and erase this stuff and see what we can use it for. Remember, forget about anomalies and central charges. I'm not going to say anything about that in higher dimensions. I haven't made the spatial background a sphere, so I'm not going to be able to make contact with that language, or even with the language of local operators. These are states on this torus that I'm talking about. Okay, so now I can do the same thing. And again, like I said, it wasn't necessary to go through all this to get it the result I'm going to write down. Now I can take the high temperature limit of the partition function on the torus. Let me do it on log. On log of z of beta. And this thing is going to go as L over B to the d minus 1. Let me see what I have here. Sorry. Let's look at the expression. One evac. So this is also going to project to the ground state. I think that's right. Let's look one last time. Yeah, looks right. Okay, so let me just get the entropy out of this guy. The entropy formula. Right, again, it's this thing, and this is going to equal d plus 1 times t to the d times the volume of the full spatial torus now times some dimensionless number, which I'll call epsilon vac. This is like the ground state energy density. Okay? So what is this, the ground state energy density on? This is on effectively S1 cross R. It's on this spatial background. Okay? And this is a dimensionless number. So the dimensions work out here. This is just a numerical factor that comes from differentiating. And there's a dimensionless number which gives you the ground state energy on this background. And because of this swapping, if it's a theory with fermions, then the fermions have to be anti-periodic along this S1 direction. You need to be careful about the usual things you have to be careful about with modular invariance in 1+1 dimensional theories.
When you write in the upper line, when you write evac, it's the statement that there's a unique vacuum state. Even though this torus is very big, you make the torus finite, so there's a unique.
Yeah. I'm making the usual assumption of gapping it out, making this thing large but finite. So maybe I should be putting squigglies in places, but that's the idea. Okay, so we have a formula. We can now check it. So I won't really do the checks. The most obvious thing is just consider a massless scalar. Okay, consider a massless scalar. You could compute its thermal entropy. You could compute the Casimir energy on this background. You'll find that they're related by this formula. So the massless scalar works. Unsurprisingly, and I'll just point it out because it has a funny consequence, which I like. You could consider, let's say a gauge field in D equals 4, just like a Maxwell gauge field. Well, in my notation, I guess D equals 3. And this just is the same calculation as this, except you stick on some polarization states. It works here, and it sort of gives the funny consequence that I'd never really heard before of, deriving Casimir's force between the plates, in QED, this classic Casimir force calculation. You can get that by plugging in the thermal entropy of a photon gas. So it relates these two things. Let's get more closely to what I cared about. Also, for weakly coupled n equals 4, it relates the thermal entropy to the Casimir energy on this background, where again the fermions are antiperiodic on the S1.
But you get not the factor of 3, 4.
No, you can't get the factor of 3, 4. Well, it's a weak coupling thing, so at weak coupling it matches, and now I'm going to talk about the strong coupling.
Sorry, why do you need to check? Isn't this obviously true by Euclidean pattern rule?
Yeah, but when people do derivation, sometimes other people are unconvinced, so then you do examples. Yeah. Okay, so now we want to do this sort of...
Could be a theory without a Lagrangian where you can't define a pattern.
No, but you're still a Hamiltonian, right?
Sounds like something Lenny would say.
Cyber
can do it
managed
without.
to abolish the Hamiltonian.
Okay, all right. So let's see. Okay, now we want to consider the ADS black brane. So I'll do it in general dimension, but of course we can get to the ADS 5 case. So the way to do this calculation in the cleanest way, I think, is to start off with the black brane with one of the directions compactified. Okay, so I'm just going to compactify one of the directions. Here's the black brane geometry. And this thing has some, if those directions are infinite, it really has some infinite Bekenstein-Hawking entropy. And so the question is, we have this formula, but what do we put here? What's epsilon vac? And the natural conjecture, especially because I wrote it in this way, is there's this object called the ADS soliton, which is obtained by a double Wick rotation of the ADS black brane. Okay, so the ADS soliton, I'll write down for you. Minus R over RH twiddle, 2 plus D plus 1 minus R over RH twiddle, 2 plus D, theta squared plus dx I squared.
And this has no horizon.
This has no horizon, RH twiddle, this is just fixed. If theta has periodicity 2 pi or whatever you want it to be, then RH twiddle is fixed by demanding that there be no, that this kind of cap off smoothly. So that fixes this value. So this is a unique, well, in that sense, you fix this RH, so it's unique in that sense. This is a single geometry. And the proposal was that the proposal by Gary Horowitz and Rob Myers, is that this is supposed to be the geometry is dual to the ground state of strongly coupled n equals 4 with antiperiodic boundary conditions for the fermions again. Okay, and you can from this object get epsilon vac. So by whatever method you like, that is a good one, like renormalizing the Brown-York stress energy tensor. You can plug into S, and this recovers the entropy of the brane. So, in the BTZ case, we had to use the central charge. In this case, again, since I don't have anomalies or something, I can either calculate at weak coupling or by an ASG or something like that. I have to do something else, and this thing is the natural thing to try and use as the ground state energy, and if you use it, it gives you the correct answer. Okay, yeah.
Can you use this technique to get subleading terms in the volume, or is it just the leading term in the volume?
Subleading terms in the volume.
It looks like you're looking at the term that's proportional to the volume of the extra dimensions when they're infinite.
Yeah. I can get in the usual parlance of getting subleading corrections that look like logarithms of the area of the horizon, that you can do, but that's sort of stupid. I mean, it's so in this language. So Stephen Carlip first did this for the BTZ black hole, and in this language you have an expression for the partition function. You have the partition function, and the idea is that you just transform it to the density of states as some integral. Okay, and in this language, the only logarithmic corrections that come about are you do this by a saddle point approximation, and the only logarithms that come from going to subleading order in the saddle point approximation. So that's sort of all this sees, but I think that's sort of consistent with the bulk, because it's there's a cosmological constant, and by some arguments that I haven't fully gone through by Ashok Sen, I think he shows that the normal logarithmic corrections you would expect directly in Z of beta are suppressed when there's a cosmological constant. But in any event, from this point of view, these are the only log corrections you get. And you can calculate it.
I thought you meant sub-extensive.
Yeah, sub-extensive corrections in the size of the extra dimensions.
Oh, I see. Is that what you meant?
Yeah.
But when I asked logs, you said yes.
Well,
okay.
He does.
These are the ones you get. I haven't thought about it.
But in principle, in your derivation, when you take this limit, you could consider doing some sort of expansion and keeping track of the subleading corrections as well.
Yeah.
In terms of whatever the parameters that govern the spectrum are.
Yeah, I think that, right, that will probably get into some more details. Okay, how much time do I have? What's going on?
Well, you have almost 15 minutes, but...
I'll just make a
fine.
comment and then I can close if there are questions. So, okay, when I first did this, I thought this is great. You can get the entropy of the black branes. I'll make one more comment. What I was referring to earlier is you can also generalize this kind of cardi type derivation, or at least getting an entropy in terms of a Casimir energy, by giving, like I said, anomalous dimension to the stress energy tensor. And that is basically related to the case of non-conformal branes. So non-conformal branes, or these other examples of holographic duality, they also have black branes. The entropy, they have normal Bekenstein-Hawking entropy. And so you can do all this for those cases as well. So those are, I'll just write down what the background geometry looks like. I mean, asymptotically, without any of the compact manifolds, it's like there's just a different scaling with R. So there's some geometries like this, which have black brane solutions, and you can generalize the calculation to get these guys as well, and that's connected to the case of non-conformal branes. And, okay, Good. So the final, any questions before I say?
Yeah, so for these non-conformal branes, is there some enhancement in the structure and analogous thing to an anomaly for the two-dimensional case, like there was for ADS3?
Not that I know.
So you still express it just in terms of some vacuum energy. And
That's right.
That may or may not be a non-renormalized.
That's right. Yeah.
Are you going to say something about how you do the scaling in this case? Or not?
No, because I'm out of time.
You have 10 minutes, no?
Well, for these guys, you know how to do these guys. The idea is that in the derivation, which I still have here, right? Okay, I'll point out really quickly. This thing has dimension d+1 in a d+1 dimensional CFT, and the way to think about it is it just has some anomalous dimension in these other theories. So to make this equation correct of equating these two, you need to put a power here on lambda, and that's basically it. And that's sort of the equivalence between the two partition functions. So instead of a normal modular transformation, you get something like z of beta is z of L times L over beta to the 1 minus theta. It's some nonlinear thing on the modular parameter. So yeah, that's what it is there. Okay, so there are two ways to sort of look at this. If you just close your eyes and say, I'm just going to assume that this ADS soliton is the ground state energy of the theory, and the whole community accepts that that's the way to go, then you stick that into this formula, and then you derive the entropy of the brane. But you can also wonder, is the ADS soliton really the ground state energy? And this is just some formula that sort of makes that connection more precise. You can view it as maybe proof as a field theory proof that the ADS soliton is the geometry's dual to the ground state. I'll just make one comment to make it clear why, in some sense, all this business was bound to work. And that has to do with kind of thinking about Euclidean gravity a little bit, and I'll be super schematic here. But one way of getting black hole entropy is by doing some bulk, or not really doing it, but imagining doing some bulk Euclidean path integral that localizes on the black hole saddle. Okay, and then you just differentiate this guy and get the thermal entropy as you normally would. And notice that, so this is quantum gravity, quantum field theory. Cardi is sort of a similar thing. This starts off as some, thermal partition function that localizes, again, I'm being schematics. Let me just go like this. That localizes on the vacuum state. Okay? And you might say, okay, great, they both localize. Obviously, that's the only way we ever compute anything. But they seem to localize on different things. And the whole point is this soliton business of constructing the state that has a negative energy and looks like a ground state. That thing's Euclidean action is the same as the black hole, because it's just obtained by a double analytic continuation of the black brane. So, in other words, the Euclidean action of the soliton is the same as the Euclidean action of the black brane. So you sort of see that this field theory thing is kind of guaranteed to work because we know that the Euclidean gravity approach works. So this object is effectively the same as this object. And you can make that more precise by being careful with all the steps. Okay, that's all I wanted to say, so I can stop.
Well, maybe a dumb question. Why empty ADS is not the ground state of the CFT? Just why ADS soliton?
So I changed the boundary condition. So this is asymptotically S1 cross the plane. Yeah.
Okay, yeah.
So, and you could explicitly calculate and find there's a negative, that this ADS soliton has negative energy, which is why this formula with the negative sign is not ridiculous. Yeah, Tom.
So the Cardi formula tells us things about operator dimensions. If I'm understanding correctly, this derivation doesn't.
No, it doesn't. I mean, you can, yeah. If you accept that at high temperature, you can sort of ignore what the spatial manifold is, and then you can sort of turn it into a sphere. And then you can sort of say that, these are like states on the sphere at high temperature, which are like local operators. And then you can think about it that way. But the full modular thing won't carry over to the sphere. It's
right.
sort of provably like doesn't happen.
The
Right.
other side of the duality can't be interpreted in terms of dimensions.
So not all of your directions are large either, right? So you can't really make that argument, can you? Because you're taking all but one of the spatial directions.
Oh, I can make that one large too. Here I was just trying to do this exact modular invariance, so I wanted to kind of make it not true. But I can make that large and say, it's really a sphere. Who cares what it is?
Well, that's dangerous because then the gap above the ground state goes away, and you're relying on it not being infinite to be able to say that you can project onto the ground state.
Yeah. But the entropy of the ADS Schwarzschild black hole when it's large is that of the black brane, so it all seems to work out.
If the gap goes away, you just need to know what the density of states around the gap is. You can probably just understand the
Yeah. The mistake might be not exponentially. It might be the suppression might be less of the error.
So usually, when you say something's a modular form, that kind of statement is most useful if you can make some statement about this global property of upper half plane. Now, what can you say about this function, this partition function as a function of tau, away from these two limits you're taking?
Sorry, away from the high temperature limit.
Yeah.
I mean, you can make whatever statements you would make about a modular invariant function.
But you need some. In order to extract some more information, you want to have some input from the theory. For example, take this equals source granules with this zero communication. I guess you will gap the spectrum, and maybe by looking at the excitations above the ground states, you'll compute some first correction to that particular function.
Is there any case where it is homomorphic in tau?
It's not only homomorphic, but there's still some things you can say, but it's not.
Yeah. This thing I think is not. Yeah, I only phrased this in like modular invariant language like a few days ago, so I haven't thought yet about what you can extract from certain theories. I mean, it's sort of. Let me make it sound a little bit more stupid. These directions are really large. So as you know from the Euclidean point of view, if you have directions on the torus getting large, it doesn't matter what direction it is, that's effectively the thing that's projecting you to the ground state. So somehow it's like, it's not the most interesting limit of the torus. But yeah, I haven't thought seriously about what you can try and extract once you think about specific theories.
Any other questions?
Eric?
So the cosmic energy in 4 dimensions, when you look at a distance away from when you take the limit when the plates get smaller, closer to each other, it's a function of the distance.
Yeah.
It's a sub-extensive part of it's not an entropy density, it's really a sub-extensive motion. And so I'm wondering, where did you look at the situation where you take the vacuum energy as a function of your compactification radius? The theta, you make one thing.
Yeah. So the vacuum. Okay. So
the scaling of the vacuum energy in higher dimensions is different than in 2 dimensions. This is what
So the vacuum energy should basically go as what here I'm calling epsilon vac times the volume over. This is the small direction, and the other directions are large. And this is how it scales.
So it scales like something.
Yeah.
Anything else? All right, thank you.